Hello, everyone. Thank you so much for attending this talk. My name is Bo Jian. I'm currently a PhD student advised by Professor Pikimenko. In this talk, I will present our work, ECHO, which is a compiler-based GPU memory footprint reduction technique for LSTM-RNN training. The LSTM-RNN, which stands for the Long Short-Term Memory Recurrent Neural Network, is a model that has been heavily used in machine translation or speech recognition. Its training, however, has been shown to be less efficient on the GPUs, especially when compared with CNN. To understand the reason behind such inefficiency, we did a comparison study between ResNet-50, which is a CNN-based model, and NMT, which is an LSTM-RNN-based model, on throughput versus batch size. We observe from the left-hand side that the training throughput of ResNet-50 saturates as batch size increases. We observe from the right-hand side that the training throughput of NMT keeps increasing with the batch size. However, such increase stops at the batch size of 128, and the reason is because the model hits the GPU memory capacity limit, and hence the batch size cannot be further increased beyond this point. We therefore conclude that the memory capacity limits the MT training throughput. We developed a GPU memory profiler under the MXNet machine learning framework. Our profiling analysis of the machine translation application reveals that feature maps, which are the data entries slashed by the forward pass to compute the gradients during the backward pass, dominate the GPU memory footprint. There are three main strategies to solve the memory capacity limit, namely, first, CPU offloading, which temporarily offload data entries from the GPU to the CPU. It has the advantage of being general, but it requires intensive use of the interconnect. The second strategy, data encoding or compression, has the advantage of low performance overhead. However, it is specific to certain model or layer type. The third strategy, selective recomputation, potentially is both general and have low performance overhead, which is the reason why we decided to pick this strategy in our work. The key idea behind selective recomputation is to trade runtime with memory. Consider this simple neural network where we have 4 operator nodes whose outputs are stashed as feature maps. Because there is a large temporal gap between the time when the feature maps are generated during the forward pass and the time when they are used during the backward pass, those feature maps have to be stashed persistently in memory, contributing to the total memory consumption, T. Selective recomputation introduces this recomputation path that brings the feature maps all the way to the front of the computation graph. This effectively reduces the total amount of persistent storage from 4 to 1. But it comes with the cost of having to re-evaluate the feature maps when the backward pass starts. However, the good news is that the recomputation overhead can be controlled if the recomputation paths only involve lightweight operators. However, our evaluation of prior work on selective recomputation shows that those prior proposals fails to deliver satisfactory memory footprint reduction with acceptable performance overhead, as we are only able to trade 1.35 times memory footprint reduction with 70% performance overhead. The reason why prior works failed to make recomputation efficient is because they did not address 2 key challenges, namely the estimation of memory footprint accurately and the estimation of runtime overhead non-conservatively. Our first observation, memory footprint estimation, states that for each recomputation to be efficient, we need to estimate its effect on the memory footprint accurately. Consider a simple example z is equals to tanh x plus y. In the baseline, the feature maps is on the output z. If we apply recomputation in this example, the feature maps again will be brought all the way to the front of the computation graph, namely x and y. We observe, however, that the total amount of feature map storage is doubled in this case from n to 2n. And to make matters worse, we still need to recompute the value of Z when the backward pass starts, leading to a double lose situation in which we are losing both in terms of memory and performance. However, if we take this compute unit, replicate it by t times, and apply the idea of recomputation once again, we observe that recomputation in this example can effectively reduce the total amount of feature map storage from t squared n to 2tn, which is an order of magnitude smaller. This hence tells us that recomputation requires analysis of the global memory footprint reduction effect, which not only involves considering the tensor shapes and data types, and most importantly, data reuse across different operators. Due to the large number of operator nodes in the computation graph, considering data reuse is a challenging task to deal with. Our second observation, runtime overhead estimation, states that for each recomputation to be efficient, we need to estimate its effect on the runtime overhead non-conservatively. Consider the fully connected layer, which is known to be compute heavy. Our profiling analysis shows that fully connected layers consume around 50% of the machine translation training time. Because of this, those layers cannot be naively put on the recomputation path because they will significantly increase the recomputation overhead. Therefore, those layers are directly excluded in prior works. We observe, however, if the layer-specific mass property is taken into account, the feature maps of the fully connected layers can be recomputed without recomputing the fully connected layers themselves. Such layer-specific property should be leveraged so that we do not lose a single chance of memory footprint reduction opportunity. From those two key observations, we propose ECHO, a selective recomputation graph compiler path that is integrated in the MXNet NVM submodulo. ECHO is fully automatic and transparent. It requires no changes in the training source code. ECHO addresses the two key challenges that we had described previously by using a bidirectional data flow analysis approach and layer-specific optimizations. Now that we have described the motivation, key challenges, and key idea behind ECHO, let's now see how ECHO performs on real DNN workloads. We use Sakai as our evaluation benchmark, which is a state-of-the-art machine translation toolkit under the MXNet machine learning framework. We train Sakai on small English Vietnamese dataset and large English German dataset, and show evaluation matrix on training throughput, GPU memory consumption, and most importantly, training time to validation accuracy. In the case of machine translation, we use BLUE score as our validation accuracy. Our evaluation platform is a single machine with 4 2080 Ti's. We use CUDA 10 with cuDNN 7.6 and MXNet 0.12 as our software infrastructure. We did a comparison study between 3 systems, namely the baseline system without recomputation, the recomputation proposed in prior work denoted as mirror, and our own compiler-based automatic and transparent approach, ECHO. To evaluate the effect of ECHO on memory and performance, we trained the 3 systems on small dataset using single GPU. We observe from the comparison between baseline and mirror that under the same batch size of 128, mirror can only deliver 1.35 times memory footprint reduction, but it comes with 17% performance overhead. On the other hand, ECHO can reduce the memory footprint by as much as 3 times, but it only comes with 1% performance overhead. Such memory footprint benefit gives ECHO the room to further double the batch size from 128 to 256. Therefore, further boosting its training throughput to 1.27 times higher than the baseline, leading to a double win situation in which ECHO is winning both in terms of memory and performance. To study the effect of echo on training convergence, we trained the 3 systems on a large dataset using multiple GPUs. We used the subscript to denote the batch size we're using, and the superscript to denote the number of GPUs we are using. We observe that although prior work, mirror, can train the same batch size using only 2 GPUs, it converges 8% slower than the baseline. On the other hand, echo only requires 1 GPU to train that large batch size, and can further increase the batch size limit from 64 to 128. Therefore, it converges 1.35 times faster than the baseline, while reaching the same validation blue score using the same number of training steps. In this talk, we start by making the observation that the GPU memory capacity limits the LSTM training performance. We pick selective augmentation as our major strategy because it is both general and potentially has low performance overhead. However, we observe that prior proposals on augmentation fails to deliver satisfactory memory footprint reduction effect. And the reason is because those proposals did not address 2 key challenges that are required for augmentation to be efficient, namely the estimation of memory footprint accurately and estimation of runtime overhead non-conservatively. We propose ECHO, a compiler-based GPU memory footprint reduction technique that addresses those 2 key challenges. Our evaluation of ECHO on real machine translation workload shows that it can deliver 3 times memory footprint reduction, but it only comes with 1% performance overhead. Such memory footprint benefit can be converted into 1.35 times faster convergence to the same validation quality by using a larger training batch size. We are excited to say that both ECHO and the GPU memory profiler tool used in this work are open sourced under the MXNet machine learning framework. Thank you so much, everyone.